So the final thing that we really need to talk about when speaking about things going in uniform circular motion is this concept of centripetal force. And in class I start talking about that, but I guess in terms of calculations it really should be the last thing we talk about. And if you remember, we've got a couple of concepts. We've got frequency, we've got period, and we've got centripetal velocity. Now frequency and period, they are very closely related. Remember, frequency is the inverse of period, and period is the inverse of frequency. So you can calculate both of those pretty easily as long as you know how many seconds it takes for an object to go around in circles, or how many circles the object makes in a given amount of time. And you just do a little bit of division. And then you can use that information, provided you have the radius, to get the centripetal velocity, or how fast the object is going around in circles. And if it was to be let out of the circle, how fast it would be going tangentially in circles. So those two concepts are pretty, I hope, easy enough for us to understand. But this third concept is really what makes the object go around in circles, and that is the centripetal force, or Fc, which is centripetal force. And for you definition people out there, it is simply any force directed towards the middle making an object travel in a circle. Okay? And this force can be anything. If we're talking about a rope, you can have a rope with a swinging bucket on it with water in it, and that rope can be making the object go around in circles. We can talk about an airplane going around in circles. We can talk about a car. And if you have a stretch of roadway, and there's my car with a couple of tires. The tires, the friction is actually the force that makes it go in circles. So the car's going to be going that way. You can talk about, with a plane, you can talk about air force being directed towards the middle. And even in big planetary systems, you can talk about gravity being the centripetal force. So we can have the Earth, and here we've got a little satellite. Just go with it for Mickey Mouse ears. But you get the general idea. We've got gravity, which can be a centripetal force. We've got tension, which can be a centripetal force. We've got friction, which can be a centripetal force. You can have magnetism be a centripetal force. Pretty much any force out there can be a centripetal force if used correctly. So the equation for centripetal force, Fc, is pretty simple. Fc, just like any other, just like anything, we're going to be dealing with a mass and acceleration. We'll get into that in a second. But Fc equals mv squared over r. And that's kind of it. You've got any object going in circles. If it is going to go in circles, the mass will be traveling at some speed and at some radius. And if all of this stuff lines up so the object is going around in circles, this is the force that it equals making it go in circles. So we can ask how much tension is needed to make some object go some speed around a circle of some radius. And that force would actually change depending on the radius or the speed or the mass. And we actually did that in lab last week, where we looked at what happens to the centripetal force or the velocity when we change other parameters of this little equation. So that's one piece, and then there's this other thing which is called centripetal acceleration, AC, which just equals v squared over r. So if you remember, F net equals ma, the mass can be gotten rid of, and you're left with just an acceleration. So if we get rid of the mass, get rid of that guy, get rid of that guy, you're left with A equals whatever is not the mass, which is v squared over r, which is how we end up with centripetal acceleration. And this is going to give you stuff like g forces and all that good stuff. So let's do a quick couple of calculations just to sort of wrap our minds around centripetal force and centripetal acceleration. So let's say I've got and this is really what we should be thinking of. Let's say we've got a mass, an object. Let's say we've got a bucket. And let's say we want that bucket to go in circles. So forgive the fact that I'm missing half of it. But let's say we got a bucket. I've got a string. And we want the bucket to go around in circles with water in it, okay? And let's say the mass of that bucket with the water, let's say that is 10 kilograms, to make it a big old heavy bucket. And let's say we want the radius of that circle. Let's say we want that circle to be big enough that I scare you guys when I do it in class. Let's say that radius is going to be 1.5 meters. Okay? So we've got 2/3 of the equation. Now I guess the third question is, how strong does this rope have to be in order for me to swing this bucket around and scare you in class? So let's say I want to make this very, very death-defying and scary. So let's say I want this velocity to be very quick. So if I want this velocity to be going fast, let's get this thing going at 10 meters per second. Let's figure out how much tension the rope needs to be able to hold in order for this all to happen. So the FC is, we don't know, but it also equals the tension. Okay, and remember that rope can break. So if we've got a certain amount of tension that the rope can handle, if you remember when you were a little kid, maybe you were fishing and you buy 40-pound test line. That means you can carry a fish that weighs 40 pounds on that fishing line without the fishing line breaking. Or why do we use chain? Well, string isn't strong enough, rope isn't strong enough. So if I'm going to do this demonstration in class, how strong do I need the rope to be in order to have all of meet these parameters? And the equation's actually once again pretty easy. Fc equals mv squared over r, and I can actually replace Fc with Ft because we're really asking how much tension does the string need to be able to handle. So the mass is 10, the velocity is 10 squared. It's going to be a very heavy duty string, and the r is going to be 1.5. So let's do a little calculation. 100 times 10 is 1,000 over 1.5. So 1,000 divided by 1.5, 666.7 newtons. And that would be the strength that the rope would have to actually deal with, which, if you care, would be about 66, about 30 pounds if you were going to be playing with the imperial units. So if I got 40-pound test line, this would all be okay. But in terms of newtons, it would be 666.7 newtons. So that's piece one. And then the other question is, well, how many G's would that, if I do this, how many G's would that water be feeling? And we can ask that because, remember, we've got a normal force going, we got the string making a force towards the middle, but also the water wants to travel tangentially. So if we're going this way, we're going to be, at any given point, the water wants to travel out of the bucket tangentially. And in reality, the sides of the bucket are creating a force on the water to keep it inside. And the best, so that's kind of what's going on with this and why it's staying in that circle, because we've got the tension acting on the bucket and the bucket's acting on the water. But we would also like to know sometimes, what's that water inside feeling? And if we remember, we're all pushed down with an acceleration of 10 meters per second on Earth because of gravity. Okay, we named that guy little g, gravity, the acceleration due to gravity. So if this bucket was just hanging vertically, and this is in the horizontal plane, this is in the vertical, this is not up and this is not down. This is, I'm swinging it parallel with the ceiling. But if we were just to now turn this and let the bucket hang, the water would experience an acceleration from gravity of 10 meters per second squared, 9.8 if you're one of the smart kids with the decimal places. But for my purposes, 10 meters per second is good. 10 meters per second squared is good. So that water is always experiencing 10 meters per second squared going down. Well, remember that acceleration is not only a change in direction, but also, not only a change in velocity, or not only a change in speed, but it can also be a change in direction. And that's why acceleration is a change in velocity, because it can mean both speed and direction, or speed or direction, or both. So what we can really look at is, what does this water feel as its change in velocity, and how literally does it feel? So if I start swinging this around parallel with the ceiling or parallel with the floor, we can look at how hard is this water being pushed by the bucket compared to, being pushed by the bucket compared to how does it feel when it's just sitting on a string on the ground. So we got FG going down. So, what we basically say is, if there's more than 10 meters per second squared of acceleration, we can actually say 20 meters per second squared would be 2 Gs, or 30 meters per second squared would be 3 Gs. And that acceleration is caused by the fact that this might not be changing speed, but it's definitely going to be changing direction. So the equation for that is this AC equals V squared over R bit here. And if we were going to be using the same scenario, AC equals V 110 squared over R 1.5, we would actually see that it's 100 over 1.5, or 66.67 meters per second squared. And if we remember that 1 G is 10 meters per second squared, 66.67 meters per second squared, times 1 G over 10 meters per second squared. Meters per second squared will cancel out. 66.67 times 10, times 1 divided by 10 will give you 6.667 Gs. This water would feel like it's being pushed 6 times as hard as gravity pushes it. So, if we were going to be really thinking about this, if I was to put a scale at the bottom of the bucket, the water would be 6.6 times heavier on that scale than it would be if we were just letting that water hang out in the bucket vertically. So that's something a little interesting to say. So we get 10, and this goes back to 10 kilograms of water all of a sudden exerts a force of 666.7 newtons on that string, because that string has to pull really, really hard to keep that thing going in circular motion. So I hope that helped a little bit, just kind of differentiate between FC and AC, centripetal force and centripetal acceleration. These are very rudimentary problems, but as long as you know the mass, the radius, the velocity, you can figure out the centripetal force or the acceleration. You don't even need the mass to figure out the acceleration. Or if you know the centripetal force, you can figure out any of the other things, V, R, or M. So it's just a matter of algebra playing around in these equations, either FC equals mv squared over R or AC equals V squared over R. It's just a matter of doing the algebra to maybe solve for V or R or FC or whatever. So again, I hope this helped. You've got homework which is due on Monday, and we've had the ability to scan that in. So I hope you downloaded it, and I hope that this will help you with that homework. Alrighty.